Okay, so we come to the last two topics in this module. One is looking at effect of medium on van der Waals forces, and then the second one is to look at what are called as combining relations for Hamaker constant. Um, so this particular picture highlights the role of medium on the van der Waals force of attraction. What you are looking at is a case where you have silica particles, okay, in embedded in air. These are the two silica particles, that and this one, and then they are embedded in air, and then they are interacting via the interacting medium in this case is through air, and the effective Hamaker constant that people have reported for this case is A is 6.5 10 power minus 20 joules. Okay. Now, the same particles when they are put in a different medium, in this case water, again the same particles interacting via water, it turns out that the Hamaker constant is about 0.8 into 10 power minus 20. Okay. So, though the this is the same, but there is a significant reduction, right, though the order is the same. Okay. There is still a decrease in the value of Hamaker constant. That means that if I were to think about calculating the van der Waals force of attraction between silica particles in air and compare it to silica particles in water, when the medium is changed from air to water, the effective Hamaker constant is lower. That means the effective van der Waals interaction is going to be lower, right. That is the gist. Okay. So, therefore, in general what is understood is the presence of any medium other than vacuum, is always going to reduce the magnitude of Hamaker constant, that in turn would reduce the magnitude of van der Waals forces. Okay. That is the gist. Okay. So, in order to consider the effect of medium on van der Waals forces, one of the approach that is followed is by using what is called as combining relations, for obtaining a general, this is a general method that is available to obtain Hamaker constant between maybe similar or dissimilar particles embedded in a medium. So, in this case you have medium as J, and there are two dissimilar particles I and K, and the Hamaker constant for this particular case is designated as A I J K. The first subscript corresponds to the one index for the one particle, second subscript corresponds to the index of the other particle, and what is in between is the medium, right. That is a general convention. So, in essence what we are going to do is to these are the important results that we are going to discuss. Okay. So, what you have is a case where you have two similar particles, particle 1 and again particle 1 interacting via medium 2. Okay. And it turns out that for such a case Hamaker constant that is A, sorry, this is 2, okay, sorry with that. Okay. The particle is designated as 2 and 1 is a medium. In such a case I can write A212 as the Hamaker constant between the species involved, that is A22, that is the particle, A11 that is for the particle, and these are Hamaker constants when the medium is vacuum. Okay. So, therefore, A212 goes as A power 1 in A11 power half minus A22 power half, okay, to the power of 2. Okay. And you could have a case where I have two distinct particles, that is particle 3 and particle 2, which are interacting via medium 1. Okay. For such a case A312 goes as A33 power half minus A11 power half multiplied by A22 power half minus A11 power half. Okay. So, we are going to look at how do we get such relations, okay, and then we will try to talk a little bit about what are the implications of these results. Okay. That is what we are going to do. So, one of the approach that has been available in the literature is to use what is called a reaction engineering approach. What you have is a schematic, okay, that is particle 2, okay, and so you should think about this case. Okay. There is a particle 2 interacting via a medium 1. Okay. Now, if you have a case like this, and if you say that look, I can imagine that for every dispersed particle there is going to be some solvent molecule surrounding it, right. There is going to be, for every particle that you have in the dispersion, there is going to be some solvent molecule surrounding it. Okay. That means you have a dispersed phase and a solvent phase. I am thinking about a reaction, okay, where I have a dispersed phase and a solvent phase which coexist together. Okay. That kind of combines, okay, with another particle in a dispersed phase, giving rise to an aggregate, right. So, you can think about this is a doublet, okay, which is formed because of van der Waals forces. Okay. And similarly, this solvent molecules again they combine to give again a doublet of solvent molecules. Okay. And so, you can also think about in the before this aggregation happens because of van der Waals forces, both the dispersed phase and the solvent phase, they are free to move wherever they want, they are kinetically independent. However, when this aggregation occurs, when it forms a doublet, they become kinetically dependent on each other. Okay. Wherever this would go, the other one would also follow, right. In that sense, there is the kinetic dependence, independence is lost. Okay. They become kinetically independent. Okay. So, what is being shown here is a pseudo chemical reaction, okay, in which you have initially you have a dispersed phase and a satellite solvent particle, okay, because as I said that in solution you will always have particles coexisting with solvent, okay, and they are kinetically independent to begin with. Okay. However, because of the action of van der Waals forces, okay, so what you do is you get in this particular process you get a doublet of two dispersed particles come together to form a doublet, and the solvent molecules again come together to form a doublet, and they become kinetically independent, right, kinetically kinetically dependent, right. Okay. So, now if you want to think about you can think about writing an expression for what is the change in the potential energy, okay, or change in the interaction energy, okay, that accompanies such a process. Okay. If delta phi is the change in the interaction energy, I could write going to the reaction engineering concept, okay, that is the energy associated with the formation of a doublet of solvent molecules and the energy associated with the formation of a doublet of the dispersed particles, okay, minus energy associated with the phi 1 2, right, and then another minus phi 1 2, right. Therefore, delta phi becomes phi 1 1 plus phi 2 2 minus 2 times phi 1 2. Okay. So, this is a general picture. I could have imagined that I could have what is shown here is looks like a spherical particle, right. But I could write a similar thing for a cube-like particle or any geometry, right. But what would be interesting to note is that if you look at each of the terms, okay, the moment I fix the geometry of the dispersed particles and the solvent molecules, phi dependence, okay, each term on the right hand side, the phi depends in the same way on the size and the distance parameters. What I mean by that is, if I were to imagine these to be spherical particles, we know that phi van der Waals, okay, phi van der Waals is going to be minus a times r divided by 6 d, right, where d is the separation distance, a is the Hammocke constant, r is the radius of the particle, right. Or if I were to think about block, semi infinite blocks, van der Waals force of attraction goes as minus a divided by 12 pi 1 over d square, right. So, that means if you all these phi 1 1, phi 2 2 1, phi 1 2, they depend in a similar way on the distance of separation as well as the size of the particles. Okay. Now, if that is the case, then what you can do is I can actually cancel out the distance dependence, okay, and in essence I can reduce this particular expression to A212 is equal to A11 plus A22 minus 2A12. Okay. I can do that because I am assuming that, or because it comes from the fact that each term here, the phi depends the same way on the size and the distance parameters, okay, and it differs only in the molecular parameters, and because it differs only in the molecular parameters, the only parameter that will be different for each of these terms is the Hammaka constant, right. That is the concept. Okay. Now, so now I am able to write A212 as A11 plus A22 minus 2 times A12. Okay. So, I know from the table that are available, I know what is A11 and A22, and of course, I can use some of the theories that we discussed in the last lecture. I can relate A11 to the dielectric constants, right, we talked about it. I can relate A11 to like say the surface tensions, right, if I know how the internal energy changes with volume at a constant temperature. Okay. So, I can there are theories available where I am either they are already tabulated, or I have way of calculating this Hammaka constants for when the species interact in vacuum. Okay. But however I do not know A12. Okay. So, A12 is the Hammaka constant for interaction between 1 and 2, okay, interacting via vacuum. Okay. I do not have that information. Okay. So, what people do is again they make some approximation. So, one of the approximation that is typically done is to use what is called as a geometric mixing rule. Okay. So, in which what is stated is that the interaction between two dissimilar bodies, okay, is given by the geometric mean of the homogeneous interactions for the two species considered separately. Okay. That means, your A12 you can actually write it as A11 A22 power half. Okay. That is a geometric mean. Okay. That is by a geometric mixing rule. Okay. So, if I use an approximation, okay, for 2 A12 I can substitute it as minus 2 A11 A22 power half, okay, and which I can further reduce it to A11 power half minus A22 power half to the power 2, right. So, that means, so this is the effective value of the Hammaka constant to be used in evaluating the attraction between like particles, okay, that is similar particles that are embedded in a medium. Okay. So, therefore, by this approach, if I know what is the Hammaka constant of interaction for the solvent molecules and the particles when they are interacting via vacuum, I can use that information to assess what is the interaction between them when they are embedded in a fluid. Okay. That is one. Okay. So, that is what one of the combining relation is all about. Now, okay. So, so there are some really nice consequence of this particular result, okay, that is when you have two particles, that is 2, okay, interacting via fluid 1, okay, your A212 is A11 per half minus A22 per half, right. So, what you can learn from this particular expression is that the effective Hammaka constant, that is A212, is always positive, okay, because it is A11 per half minus A22 half whole square. Therefore, okay, this is always going to be positive regardless of the magnitude of A11 and A22. Okay. That means, if you take identical particles, okay, which was the case, right, we took two identical particles, they are identical in terms of surface chemistry. Okay. If you take such a case, then they exert a net attractive force on each other due to van der Waals forces in a medium, okay, and that is also true for also in vacuum as well. Okay. The other important result that comes out of this particular formula, we already discussed it. So, embedding a particle in a medium generally diminishes the van der Waals force of attraction, right, because you have a difference term here, right. If A11 was some x and if A22 was some y, okay, because you have a difference term, okay, your A212 is going to be smaller, right. A212 is going to be smaller, therefore, A212 is going to be smaller if you compare the particles being in vacuum, okay, right. So, if this is A101, if you want to call it, make it more clear, 0 for vacuum minus A202, okay, again, okay, for vacuum, right. Okay, this is van der Waals, this is interaction between the same particles in vacuum, okay, that is the interaction of the solvent molecules, therefore, okay. So, the magnitude of A212 is always going to be smaller than A202, that is A22, yeah, okay, or A22. Okay. Therefore, embedding particles in a medium generally diminishes the van der Waals force of attraction between them. Again, you can take some examples. If you take A11 is equal to so much and A22 is equal to so much, then A22 turns out to be a power 10 power minus 21 joules, almost 2 orders of magnitude less than the individual particle. Okay. See these relations that we are trying to write up, right. Okay, or let me go back to the table that we had put up. Okay. So, we have this table, right. What you have is list of different materials and different Hamakova constant, right. Whenever you see a value like this, okay, A 10 power whatever, this number, right. If nothing is given, you should assume that these are Hamakova constant of interaction between acetone molecule and another acetone molecule which are interacting via vacuum. Okay, that is what is, okay, that is your basis. Okay, and the theories that we talked about, right, like for example, so now, but however, you could, or for example this one, right, a gold particle, that is a gold is what you have, okay, 45.3 into 10 power minus 20 joules. Okay. Now, if you want to work with like say gold particles, Ag, and if you want, if the medium now is not vacuum, okay, this is the value when the medium is vacuum, and if they are in water now, how would you calculate what is the van der Waals, the effective Hamakova constant, right, that is what we are after. Okay. It turns out that for this particular example, okay, okay, your A gold interacting via water, okay, is going to be equal to A water half minus A gold half whole square. Okay. So, A gold you can get from the table that is there, A water also you can get from the table that was there. Okay. I can actually essentially get what is the Hamakova constant for interaction of gold particles via water medium. Okay. So, the first implication is that the effective Hamakova constant, especially when you are dealing with identical particles, okay, is always positive. Okay. And embedding the particles in a medium generally diminishes the van der Waals force of attraction between them. The next one is, you could of course have a case where A112 is equal to A22. I could design an experiment where I could choose a solvent such that A11 is equal to A22. Okay. Therefore, you could have a case where the van der Waals force of attraction indeed could be 0. That means, this condition essentially corresponds to no net interaction between the particles. Okay. Therefore, it is possible to tune the solvent or the medium, okay, and I can essentially get rid of van der Waals force of attraction. Okay. And one of the important consequence of that could be, now that I choose a solvent such that the the van der Waals force of attraction is not there. Now, if I choose such a solvent, that is, if A11 is a Hammaka constant for that particular solvent, now I know that I can relate A11 to 24 pi d naught square gamma, right. If I choose a solvent, I can actually because I know the surface, if I know the surface tension of those fluids, I can easily calculate A11, okay. In turn I can get A22, okay. You could actually use this approach for, so what I do is I take a particle, put them in different fluids and identify a fluid where A11 is equal to A22. If I achieve that condition, and because for solvent for the solvent molecules, there are easier ways of getting the surface tension, which in turn will let me calculate A11. If I know A11, the fact that A11 is equal to A22, I can exploit that to actually calculate the van der Waals for the Hammaka constant itself for the particles of interest. Yeah.
We should know, right, A11 equals to A22 before that.
Yeah. So what you do, I mean, yeah. So yeah, you should know that condition. For example, yeah, this is a kind of
Or we can make it that way.
what is it? What is it?
We can make it that way. So
Yeah, I mean, this is an approach that one could use. That's what I'm trying to say. Okay, this is an approach that one could essentially use to calculate. For example, if you have a particle fluid combination, and if you know that, look, there is no other type of interactions. For example, like say electrical double layer interactions, steric interactions, other kind of interactions. If you know that the only interaction that are present are van der Waals. Okay. Now, if you have such a dispersion, and if you see that they are very highly stable, okay, then that could be a case where your phi van der Waals be 0, right. Now, if you have a condition like that, so it could give you a way of actually calculating what is A22, okay, by that approach, okay, is what I was trying to mention.